Okay, all the walls are clear. All right, so we're gonna still play with the same iris data set. We're gonna try to use scikit-learn decision trees, look how they are built, what's the logic. This is kind of warm up for homework 2, where you'll be implementing your own decision trees from scratch. So I just took this chance to answer a lot of questions ahead, because I'm sure you're gonna have a lot of questions in homework 2. So there's always a helper files here. So we have the plot and decision surface. That's it. Okay, so it's usual libraries, NumPy, matplotlib, and scikit-learn. We're going to import the iris dataset. And, okay, I'm doing standard scalar here just to show you how it's used. I think we have already used it before. Decision tree classifier, and then plot tree. So plot tree will be a function that will display the decision tree, okay? All right. Oops. I'm not used to this microphone, but okay. Okay. So the first thing, we just take the our data, x and y, the features and labels, okay? And then we use the standard scalar. So what the standard scalar does is that it goes through each column of x, and you subtract the mean and divide by the standard deviation, okay? So the usual formula with all these pre-processing modules is that you do basically, let's call it std scalar, and this is the usual way. So you do std scalar, fit, x, and then you come to here, std scalar, dot transform, okay? But as previously, we just did it in one line because we don't need standard scalar for other steps, so we only need it once, so you can just do it in one line. And so what does this standard scalar does exactly? So let's look at it. This is my x here. Okay, we have 4 features. So first thing is we need the mean. So I'm going to do the mean of the columns of x. So in this case, it's going to be axis equals 0. Sorry. And then we need the standard deviation. So it's going to be MP std x and then axis 0. Okay. All right. So this is basically respectively the means and the standard deviation of the column of x. All right, so once we learn these, we can just transform it ourselves. So we can just do x equals x minus the mean, okay? All right, but this is 2D, this is 1D. So I'll just add one axis to make sure I don't get any errors. So I can just do this trick. And the same thing here. So I just divide, okay? Oops, yeah, I need to do it the other way around because I'm doing it column-wise. Okay, and same here. Okay, let's just look at the first 2 rows. This is what I get. Now, if I just use the standard scalar, okay, it's the same thing. Okay, so this is exactly what's happening inside standard scalar. So when I call the fit here, the standard scalar basically computes the mean and the standard deviation, and it saves them. So once I call transform, it will apply this, okay? So just to help you, this is the fit step, and this is the transform step. So the mean and standard deviation are the ones that we learn from the x that we provide in fit. So if I have like x2 here, so the mean and standard deviation is going to be applied to x2 are the same ones that I have computed during the fit method. Okay, but here we just have one x, so it's fine. Okay, all right. start. Okay, we have some drawings here. Try to change the colors to make it a little bit better. Okay, so the Iris dataset has 4 features, and here we have the 6 possible 2D planes. Okay, so we have 0, 1, 2, and 3, C, 2 out of 3, so the number of combinations is going to be 6. So we have 6 possibilities. Okay. So the blue class, the Setosa ones, are usually easy. You can learn them, you can isolate them perfectly using the perceptron from homework 1. But once you move to the other ones, you have to be a little bit tricky. In our case, we'll be using this one, this plane, for the decision tree classifier. Okay, I hope the majority have access to the notebook, so I'll give you like 2 minutes to use decision tree classifier that's imported at the top. So this is the same thing as rich classifier and KNN classifier that we have used in homework 0 is the same, fit and predict, okay? You don't have to understand what's happening inside, it's all the same. You don't have to provide any parameter at this level. So, okay, go ahead. It's not on Canvas? It's not on Canvas. Okay, 1 second. All right. Repo is public. So you went to branch lab 2?
Yeah, and I can't clone it.
You can't clone it?
Yeah.
Okay. Oh. Yeah. So just if you want, okay, just 1 second. Give me a minute. Wait. It's the same as lab 1.
I used Canvas to download lab 1, so I didn't use.
Okay, so I guess it was not. All right, so 1 second. Okay. So now you're going to find Wake 3. I forgot to activate it. You can also go to Files. So this is the Files part. And you're going to find Labs.
Unfortunately, I don't have
It should be visible.
No.
Okay, let me see.
Oh, yeah, my bad.
Yeah, because I made sure it's visible 2 days ago. So 3 days ago, it was not. Okay, let me know when you have the Jupyter notebook. Good? Nice. All right, so you're out of time, so I'm going to do it now. I have the plots here. I'm just going to use CLF decision tree classifier. fit X and Y. Okay. And then I will do helpers. I think plus decision surface X and CLF X, and X is basically helpers. Then plot iris X and Y. Okay, I always forget the other plot decision surface. Okay. So the error here was, oh, okay. So I did not use features. I have to use the features 2 and 3, as I said, since this one has 4, and the same thing is going to be here. Okay, and same here. And I don't need this one, so let's just agree on this here. There you go. Okay. So I chose 2 and 3 on purpose because they're pretty easy, and you can see here that we learn perfectly, we fit perfectly the different samples, and it's expected because we haven't specified a max depth for the tree, so it's gonna just keep branching out until all the samples are fit perfectly. Okay?
Scroll.
Yeah, I mean, this is just a plot, nothing yet. So here I'm just going to display the tree. Okay? So I just do plot, tree, and CLF, my classifier, and I do plot show. All right. Perfect. So this is my decision tree. The first, at the root node, we are splitting based on the first feature, 0. So in this case, it's 2, since we took 2, 3, so 0 is 2 and 1 is 3. And at this node, we have 150 samples. That's the entire number of samples we have in our training data. And based on this split, so if we split the data based on the value of the first feature, we're going to end up with 50 samples on the left and 100 samples on the right. Okay? So which ones do you think are going to be on the left side? So if we go to the plots, 2 and 3, yeah, exactly. So if we take the value around minus 74, we can perfectly isolate the Setosa class. So we have 50 samples per class. So that's basically what the root node does. So at the first level, we get rid of the Setosa class. Now on the right side, we have 50 from Versicolor and the other one from Virginica. And then we keep branching out, okay? And you can see that the final nodes, which one is it? Yeah. So the final node here has basically pure leaves, which means that it contains only one class, except this one here. All right. And why do you think the decision tree stopped here? Was it?
This is only 3 samples.
Uh-huh. Yeah. So there is a, if you go to scikit-learn decision tree, oops. We're going to check.
That was just the same
All right, so one thing I forgot to mention is that you might get different results. And the reason is decision tree is not completely deterministic. There's some shuffling, there's some randomness there. So if you want to make sure everything is good, you can just do like random state equal 42. Let's agree on this one. Okay? So in this case, we can all agree that we're going to all get the same tree. All right. So there's this parameter called min sample split. Okay. So that's basically the number of samples that I should have in a node before I split it. So if I have basically one, I'm not going to split anything. And my guess, and we can check later, is that when we reach here, if we split based on any value, we won't get any reduction of the Gini index. Okay. So far we explained what the split is, what samples means, and what value means, but what's the Gini index means. And that's the next step, just to give you a flavor or a taste of what's happening. Okay. So imagine now I have some categorical variables inside a node. In this case, it's the class or the labels. And I have k labels, okay? And I have an array, which is, you can look at it as y, and contains a set of values between 1 and k, okay? Then we can compute what we call the ratio or probability. And the ratio here, for example, Pn is the ratio of value n inside that array. And the Gini index is just 1 minus the sum of the square of those ratios. Okay, it sounds a bit magic, but it's not. You can look at those as probabilities, okay? So P1 is the probability of observing value 1, P2 is the probability of seeing value 2, and Pk is the probability of seeing value k, okay? And since we know these are probabilities, we know that the sum of the Pn's is equal to 1, okay? And so I'm not going to stop at question 3, but that's basically it. So 1 there, I can replace 1 by the sum of the Pn, and then I can just merge the sums. It's going to be Pn minus Pn squared, which is Pn, multiplied by 1 minus Pn, okay? But we're not going to use this one. Now we want to implement the function Gini, or Gini index, that will compute those values. I give you 1 minute to think about it. You can just consider A as equal to Y, okay? So you can do this multiple ways. You can either use the counter class from collections library. I prefer doing it in NumPy because it's much easier. So if I do np unique of y, return counts equal true, this is what happens. Okay, it will give me the unique values and their number of counts. And for me, I only care about this one. I don't care about the values. You can just put any values you want, okay? So if I take that one, I'll just call it counts. Now the probabilities are going to be counts divided by the sum, okay? It's going to be np sum of counts. So it's just 3, 3, 3, 3, since they are equally probable. So these are the pi's or the pn's that I have here. So now I can just raise everything to square, and then I can sum. Something is weird. Oh, 82. Yep. Okay, and then I just do np sum, and then 1 minus 1. This, all of this. Okay, so this is the Gini index for the entire data set. So I'll just copy and paste this one, and I'll change y with replace Gini index. All right, and here's going to be A. So this is my Gini index function. So the Gini index or the notional Gini index comes from economics, I think microeconomics to be specific. And it's a measure to quantify the inequality or the level of inequalities in a certain set. Okay? So let's just take the example of binary labels. We either have zeros or we have ones. So if you go to the expression of Gini, you just replace P0 using P1, or the other way, it's always symmetric. And you can prove that in this case, Gini A is going to just be 2P0 multiplied by 1 minus P0. P0 is the probability of observing the class 0. Usually it can look like P0 is the ratio of population that is below the poor threshold, which is basically the poor population. P1 is the rich ratio of population. Okay? So here we're just going to have the Gini in function of P0, which is going to be Gini A equals 2 P0, P0 multiplied by 1 minus P0. So this is the curve that you would see if you plot this in function of P0. So what happens here is that Gini index is going to be 0 if we only have zeros. Okay? Sorry, P0 equals 0, then we only have ones. So if the entire population is rich, we have Gini index equals 0. If the entire population is poor, it's also 0. If it is equally distributed, that's where the Gini index is maximum. All right? If you're interested in this notion from economy, you can look like United States. Let's go to Wikipedia, and let's just look for Gini. Yeah. So the Gini index of United States is around 46.9. Sorry, it's not clear here. So let me show you it. There. It's quite high, so there's lots of inequality. Let's look where I come from. Morocco. Yeah, it's a little better. It's a little bit better because everyone is poor. Yeah. But in microeconomics, it goes from 0 to 1, so it's not from 0 to 50%. Okay, so it's a bit different, but the scale is the same. I mean, the notion is the same. Okay. So if we go back to tree, the goal here is that to reduce the Gini index when we move from the parent node to the child node. Okay. So you can see on the left node, the first left child, we have Gini equals 0 because all of them contain only one class, right? When we move to the right one, we're getting Gini equals 0.5 because the population is equally split between the versicolor and virginica. So that's basically the value that we have seen when P0 is equal 50%. Okay? And the goal here is that we split so that the Gini index is reduced, but it's not just one. You can have multiple splits that reduce the Gini index. The goal here is that at each node, we're going to take the split that will minimize the Gini index. Because you're probably going to move to 0.8 or 0.6, 0.5. So we're going to take the one that gives us the minimum, not just the decrease, the Gini index. Okay? Well, you're saying, well, okay. I don't know if you have seen it in lecture, but how do we compute the Gini index of the children? We know the parent is easy, but now you have split the population, but you're still looking at the Gini index of both the children. And that's what we call, okay, 1 second here. I'll come back to this later. Okay, forget about this one so far. Okay, so assume here we have samples that went to the left child and samples that went to the right child. So the Gini index of the split is proportional because we're just going to divide by the total number of samples, but it is proportional to the number of samples in the left multiplied by the Gini index to the left plus the number of samples in the right multiplied by the Gini index in the right. Okay? And let's do this. Okay? So, if we go back to the tree, the value that we split on is minus 74. Okay? Let's agree that 74. So that's going to be my threshold. Okay? So let's call it threshold minus 0.74. So the left here is going to be the features that are less than the threshold on the 0th feature. And the right side is going to be the other ones. So in NumPy, you can just do tilde left. Threshold is not defined. What about now? Okay. So this is the exact value that we got. Gini index 0 on the left and 0.45 on the right. Okay. And the way I have seen before, you can just do how many members I have on the left. It's going to be sum left and MP sum right. Okay. So it means that my weighted or the split Gini index is going to be 50 multiplied by Gini left plus 100 multiplied by Gini right. Okay. I'm going to divide this by 150. All right. So this is the Gini index of the split. All right. Now we want to prove that you cannot do better than this split. You cannot find another value or another threshold to split on where you can get less than 0.44. Okay. So we are going to look at the possible values of x0. Okay. And yeah. So here I'll just return what I have done here. It's the exact same thing. Okay. Okay, you missed here y, and here it's y. Okay, it's 33, okay. I'll just return this, but I don't need to divide by here. And this is, as I said, going to be sum of right, and here's sum of left. If you have any questions, anything is kind of weird, let me know. Let me show you thresholds. So what this does is that it just shows you the unique values in x0. So I don't have to split twice on the same value. So I'll just try to take the unique values. Okay? So these are the unique values. So here I'm going to compute the weighted Gini of the split for each one of these values. Okay? So here I define these thresholds here. So now I'm just going to loop and do the same thing. So I'll just copy this one. So threshold is going to be on my t here. And this one is going to be the t. Okay. And now I just do t to Gini of t equals. And just weighted Gini of y, left and right. And I'll print the values. And this is what I'm getting. Okay. Anything weird? So I get the best threshold for my Gini is minus 0.43. But if I go to 3, I'm seeing minus 0.74. Okay, so the reason is how decision tree, scikit-learn decision tree chooses the thresholds. Okay, So the way I took the thresholds is I just went to the first feature and I took the unique values, right? But what decision tree in scikit-learn, it does not look at the unique values. It will look at the midpoint between the unique values. Okay, so one of the unique values for feature 0 is minus 43, and then we have minus 105. Okay, so in scikit-learn, it does not take the values. It will take basically the mid value between these two. So I can just make sure that it makes sense. So I've taken the midpoint of these two, and I divide by 2. That's the threshold that scikit-learn uses. To make it easy, there's a simple trick, which is I can just do minus 1. Is it minus 1? No, it's 1 plus, then minus thresholds minus 1, and then divide by 2. So there's a problem here. Oops, it's going to be plus. Okay. So instead of taking the unique values in x0, I'm going to take the midpoint between each two contiguous values from the unique thresholds. So if I use this one, I just run the same thing, and now I'm going to see the exact value. Okay, so what I did here is that I went through the unique values in x0. I take the midpoint between two consecutive values, and then I computed the weighted Gini index. And this one is the one that gives me the lowest weighted Gini index. And that's the point I'll be splitting it on, okay? So in decision tree, it did not choose 0 just randomly. It actually compared the same. It compared the Gini indexes you get by splitting on 0 and the ones you get from splitting on 1, and it finds out that 0 is the best one. So that's why we split on 0. So the left side is pure. So Gini index is 0. We don't have to do anything. Now we move to the right side and we repeat the same logic. Okay? So you can just look at you can just assume that the data set only has 100 samples, 50 from each of vesicular and virginica, and you can look at this as a new tree, and you build it and you branch it. Okay? So you stop when either the Gini index is no longer reduced, or if the nodes become pure, like you see here. Okay. So when this case happened, it happened usually when you, for example, you have let's see, you have like 2 points of vesicular and you have a virginica in the middle. Okay, so it doesn't matter where you put the split, you're never gonna end up with pure ones. Yeah.
So I don't understand what the relationship is between the weighted Gini and the Gini index. Why is the weighted Gini? Why can't it be negative when we're working mostly at a positive set?
Why weighted Gini cannot be negative? Because it's a function of probabilities.
But it is negative, so I thought that it wouldn't be able to be negative.
Wait, where is it
We
negative?
have negative 0.74, didn't we?
That's the threshold.
Okay.
No.
What is that then?
Okay. So let's look here. This is the data set we are working on. We are working on 2, 3. All right. Okay. So what this does is that I'm going to look at the 0 here, and you have the threshold 1. I mean, the 1 feature and 0 feature. So here we just go through the values of the threshold, which is like at which vertical line should we split the data. So minus 74 is around here.
Oh, I see.
So if you split here, you have a node, the left node, that will take all the setosa. So that's why you get 50 samples. But the other one, you're going to get the other 100 samples. Okay. So the split here is done on feature 0. Okay. So once you're done with this, now we do the same thing here. Okay. So you can see here that if I choose like minus 0.5 on feature 1, I'm going to get the same thing. I'm going to get the same Gini index because I'm going to get the same samples on the left and right. Right? So in that case, we just keep the first one that we had. All right. So what I'm saying is, once we done that, we move to the same logic. So at this time, we only have 2 classes, and we do the same thing. We go through feature 0, feature 1, look at the possible values, split on all of them, and for each one of those, compute the Gini index, and keep track of the one that gives you the best weighted Gini index. Yep. So it's a recursive logic. This does not give you the optimal tree. This is basically a greedy algorithm. Finding the optimal tree is NP hard, if you know what that is. It's basically, it means that you have to try all possible combinations through the whole det. Okay? So if it's just a level 1 and you have 10 thresholds per feature and you have 2 features, so that's basically, you have to do 100. And once you move to second level, it's 100 multiplied by 100, so it's 10,000 possibilities, and you do the same thing. Okay? Using this logic, which is greedy, you only have 100 comparisons at each level. So it's just going to be 100, 200, 300. So it's a greedy algorithm. It's faster. If you want to find the optimal tree, you have to test all the possible combinations, which is a function of the depth of the tree. So the optimal one is basically exponential time. All right. If you want to go deeper and see what exactly happens inside scikit-learn, it's very difficult. The official implementation is done in Python and C++, so it's difficult to decode, but you can try to figure out what's happening. Okay. So you can go to CLF, which is a classified -tree underscore. It's going to have children left, children right, threshold, and feature. So the threshold here, that's basically the threshold that we have got. Okay. If you have questions how to decode this, I can answer them later. But this is how scikit-learn decided to implement the algorithm. Okay. So here it just says that for features means that the first node is split on 0. The second node is a left child, so there's no split, so they do just -2. When you see -2, it means that we're not splitting. If you go to children left and children right, if you see -1, it means that it's a leaf node. It does not have any children. And so I'll let you reverse engineer scikit-learn. If you want to go really deeper into their implementation, you can just go to the source code and okay, it's not in ClassesPy, it's here. If you're not familiar with C++, C or Python, it's just easier to implement your own thing. It's really difficult to decode. So these are just the definitions, and then here, this is the implementation of the builders. Okay. If in your homework you say, okay, I'm just going to copy scikit-learn, good luck. All right, we have gone through all of those. In the last 5 minutes, I just want to mention one thing. So in this notebook, we only have one set of samples, which is X. It has 150. We don't have validation, and we don't have test. And now I ask you, well, I want to find the best decision tree for this data set. But to do that, you need validation, at least, a validation set. So the trick here is that we can use what we call the k-fold cross-validation. So what it means here, let's say I'm going to split on 5. So I'm just going to split the data set into 5 parts. And at each iteration, I'm just going to keep 1 as a test set and the 4 other parts as training sets, training data, okay? And I try all the possible combinations, and then I average over these, okay? So this is just the k-fold. I'm just going to do the usual imports, okay? Here I'm just showing you how actually it works. So imagine my X is just 5 samples of 0 to 4, and then I get the indices. So the training indices contain 4, then 0, then you exclude 1, 2, 3, 4, okay? So now I'm going to do it another way. Just go and try to use my original x here. I'm just going to scale it. And yeah, that's pretty much it. That's everything I need. Okay. So here, if I split this time on x, it's going to be quite large. So each time I'm going to have divided by 5, it's going to be 30. So I'm going to have 30 samples in the validation set. Okay. So now what I'm going to do, just create my CLF classifier, decision tree classifier. Okay. So I'm going to fit it using my training part, which is going to be train index, and then y train index. Okay. And let's say accuracy or ac equals CLF, I think score, if I'm not mistaken. Tier index. Sorry, this time going to be test, and y TS index. Okay, fingers crossed. Yep. Okay. So I'm gonna, at each iteration, so I have 5 iterations here since the number of splits is 5. So at each time I fit the classifier and I get the accuracy on the test data, which is 20% of the data. Okay. So my accuracy will be the average of these. And that's basically what I'm going to do in cross-validate K. And in this case, K, I'll be limiting the depth of the tree. So last time there was no bound. So the tree just keep branching out until the leaf nodes are pure. But in this case, I'm going to try to, I usually like just to do accuracies like this. So K will be the parameter that I'll be having here. And if you go to documentation, it should be defined as max depth. Okay? So max depth equal K. Oops, I was working here, so I'm just going to stay here. And accuracy is this, and now I'm just going to implement add the accuracy, and now I'm going to return the average. Okay. So now I'm going to try different depths from 2 to 5. And that's the average. So it seems like 2 and 4 are pretty much the same. So it's up to you to choose which one. You can do even further, which means that you can even have a validation and a test. So in this case, you can just have inside, like, you can have a split inside a split. So inside the K-fold, you can then just take the training set and split it into training validation, and then you can keep the TS index as the test set. It's up to you. But this is the minimum that we'll be expecting, okay? There is one catch here, which is that when I split the data, you might have only like label 0 in the test set, okay? So to make sure that you have the same ratio of labels in each of these sets, so in this case we had like 33% from each class. So make sure that the test set is also 33%. You use what we call stratified K-fold. Okay, so it's the same thing as K-fold, just have different names. A name, because in this case, the splits are made so that the ratio of classes between train and test are the same. This is important if you want to make sure that one of those models you have chosen is not biased towards a certain class. Or imagine like I have only 10 samples from class 0. So in this case, there's a high probability that one of those splits will contain all those 10 samples. So I'm going to make sure that I see the same classes in the training and the test. All right. So times is up, I guess. Any questions? Stupid question?
Yeah.
Okay.
What does it mean when you had none, comma, colon, or you would have
So the,
variable, comma, colon in those brackets?
okay, so that's the NumPy operation. So when I do none, it means that I'm going to add a fake axis at the beginning. Okay? So, 1 second here.